There's no complete result that tells you that it's no relation to something but it's context. What is the question about the underlying context? So I think we can know coverage, but maybe it's better to ask. You won't get to the next week.
I call Shrikant.
He is online. Maybe just drop him a message so I can just send him out.
Yeah. Can you ask him to try and share slides?
Yanir, can you hear us?
Yes, can you hear me?
Yes. So you can hear us, right?
Yeah, I'm just using two laptops here, so I'll try.
Do you have slides? Do you wish to share your slides, or do you have a notebook?
Yeah, so I'm gonna use 1 second, let me turn on the camera. Oh, I cannot turn on my video, so it doesn't allow me.
Permission maybe needs to be granted. So I think permission needs to be granted to share, turn the camera. Video.
Let me try again. Okay. Yeah, it says you cannot start your video because the host has stopped it. So.
We have permission from.
Share screen and slide.
Is it for both? One from. We share whiteboards also.
Just try to share screen just to check. Share your screen.
How about now, Yanir?
Okay, stop.
So he's able to share. So he just shared his screen.
So Yanir, do you want to try sharing your screen again? So we can see you. We can see you. That's it, right?
Yeah.
We can see you, but I don't know if you're sharing something right now or not.
Yeah, well, yeah, just let me just start the other one here. Okay.
Some week and another one.
We're chatting.
Oh, okay, I know what's going on. It's upside down. 1 second.
Yes, yes.
Now I need to share my screen. Okay, I think now it should be okay.
You can see.
Can you see the page?
Yes, we can see it. Can everybody in the audience see this? Or would you like it? Yeah, is it possible to zoom in a little bit? A little bit larger?
Is this okay?
Is this legible? Is it fine at the back? Okay.
Yeah.
The problem is that then it's going to be quite hard to see the whole page, but yeah, that's okay.
This is fine? Yeah, okay, this is fine. And before we start, Yanir, would you prefer your questions at the end, or can we interrupt you if there's a question in the audience?
Yeah, anytime. Anytime, of course, yeah. Yeah.
Get started. All right, so it is my pleasure to introduce our second speaker, Yanir Rubinstein from University of Maryland, who has been kind enough to deliver this lecture via Zoom. And we'll talk about Mahler and Bourgain's conjectures, convex meets complex. So please go ahead, Yanir.
Okay, so thank you so much for the opportunity to speak, and it's long been a dream for me to go to India, so I'm really sorry I'm not there. Hope to make it another time. So yeah, so like you said, please feel free to interrupt at any time. Okay, so I'm gonna maybe zoom a little bit out because it's just for this slide maybe. Maybe people can sit a little closer, but it's just a lot of things in this slide. So okay, so I just want to establish some notation first. Okay, so this is this box here. So some of this notation might be different from the one in Elizabeth's talk. So I just want to make sure we understand the notation I'm using. So we're looking at convex bodies in Rn as before, and these are just all the convex bodies. These are just convex bodies which have zero in the interior, which is the usual thing to assume. If you want a polar body to be compact, and then K with a little s subscript, that's just the symmetric bodies. Okay, and then here maybe some non-completely standard notation. So this is the LP ball in dimension n. This is the usual in L infinity, or just the cube. And then this is the simplex with one of the vertices in the origin, and this one is the simplex with barycenter at the origin. And the EIs are just the usual unit vectors. Okay, so now the polar body, this is the same one as the previous talk. Okay, and now M of K, this beautiful M here, this is just our convention for our normalization, let's say, for the Mahler volume. So we multiply by n factorial. Okay, and the reason to do this is just that then Mahler volume becomes tensorial. So if I take M of K times L, it's going to be equal to M of K times M of L with this convention. Okay, so the Mahler volume is very central object. I'm going to talk about it in a second, but this is just a notation. This is just the notation for Euclidean volume. Okay, and then here we have the covariance matrix associated to a body. And this is not standard at all. So I just mentioned this, maybe emphasize that C of K is the volume squared divided by the determinant of the covariant matrix. It's also the isotropic constant Lk to a certain power. Okay, so we just prefer to use this notation because then we can phrase Bourgain and Mahler conjecture basically in the same way. Okay, so they look really similar when you use this quantity. And if you notice this in this convention, this functional has units of volume squared, basically, which is what Mahler is also volume squared in some sense. Okay, so here the Lk is the isotropic constant. It's defined. So it's really, I didn't have any space here, so I'm sorry, but basically I assume that you've seen this before, but I'll just say this. So you put the body, there's a unique way to put it in a position which is called the isotropic position. So there's this unique affine transformation T, which will make the barycenter to be at the origin, the volume to be 1, and this integral to be a unique constant no matter which direction you look at in the unit sphere. And that constant is Lk squared. Okay, so a lot of notation, at least we have that under the belt now. So okay, so then one of the most fundamental questions in convex geometry is the so-called symmetric Mahler conjecture. Okay, and so it predicts certain upper and lower bounds for the Mahler volume of any symmetric convex body. Okay, and so the upper bound is it was conjectured by Mahler to be attained by the 2 ball, and the lower bound he conjectured to be attained by the 1 ball or the infinity ball. Okay, so here there's some pictures of these minimizers, maximizers conjecturally. Okay, now Mahler also came up with a non-symmetric version of his problem in a paper from the same year, basically. So I read a little bit about the history, and it seems that he suffered some bicycle or car accident. Maybe he was riding a bike and he was hit by a car or something like that around the mid-30s. And then he needed to recover, and so he went to the Swiss Alps and spent 2 summers there to recover. And he was basically a number theorist, but so you could ask, like, how can we study these questions in convexity? Well, actually, these Mahler volumes were related to some problem in convexity for him in problem number theory. So counting lattice points and things like that. And then he couldn't really concentrate on any deep mathematics, like you would say, number theory. So he did some fun little project involving shapes in 2 dimensions, and he came up with these sort of inequalities in dimension 2. And then he sort of convinced himself, okay, I'm feeling better now, I can go back to do math. So he wrote these papers, and the rest is history. So now the non-symmetric version is basically the same thing. Now we just instead of looking at upper bounds, we're just looking at lower bounds. Okay, and the reason is just that for symmetric bodies, we're really fixing the barycenter of the body at the origin just by the symmetry condition, and for general bodies, we're not, and so the Mahler volume can be really as large as you want. So there's no meaning to talk about the upper bounds. Of course, you can remedy this by looking at infimum overall translations and things like that, but just the clean version, state like this, doesn't have an upper bound. And then the lower bound should be the simplex with barycenter at the origin. So this simplex. Okay. So Mahler didn't exactly state this conjecture, but he did everything except state that. He basically stated the problem, and he proved this was true in dimension 2. And in the same paper, he also proved that this conjecture, the lower bound, holds in dimension 2. So that's kind of the history of the Mahler conjecture in a one minute history. Okay, and so for the
Yanir, there's a question.
Can you hear? Yeah. So upper bound in the non-symmetric case, is it that it doesn't exist, or it's
the upper bound? So if I take this body here and I translate it so that the origin approaches the boundary, the volume of the polar body will go to infinity. So the Mahler volume will go to infinity.
okay?
Yeah.
Thanks.
So yeah. So here we don't really care about the upper bound. In fact, the upper bound that holds for the symmetric bodies holds for all bodies if you add this condition of infimum overall translations of the body. So I'll mention that later. Okay, now the reason I wanted everything on one page, I know it's a little bit condensed, but I just wanted to show really the nice analogies between these conjectures if you state them in this way. So here, if we look at the C functional, then Bourgain's conjecture in its sort of sharp form states that the lower bound should be attained by the cube, and this is among all symmetric bodies, and then should be attained by the normalized simplex among all bodies. Okay, now these constants are not extremely important, except the fact that they have certain exponential behavior. So they behave like e squared to the n here, and here this is like 12 to the n. Similarly for the Mahler conjecture, you can derive sort of like the exponential type behaviors. Now, it is really interesting that when you state these things in the sharp form, they actually have some connections, and this was first shown by Klartag 2018, showed that the non-symmetric Bourgain conjecture in this strong form implies the non-symmetric Mahler conjecture exactly on the nose. It's really a nice nice paper, a nice observation, and it's been given a short proof recently. So in a paper by Solanis and co-authors. So I highly recommend those papers actually. Okay, so any questions before I move to the next slide? Okay, so all right, so going to the next slide here. This is progress. Okay, so this is a very incomplete list. I am not really an expert on this topic. I feel kind of an outsider, so I apologize in advance for any omissions. But just to really give the general feeling of what's been done. So about 10 years after Mahler, Santalò proved the upper bound in a sort of strong form, the one that I didn't state with the infimum over translations and so forth. And this is where he introduced the famous Santalò point. So that is the point that achieves the minimum over translations, basically. Okay, and then yeah, I didn't really organize this chronologically, but yeah, so Mahler, as I said, proved the conjecture for dimension 2, both in the symmetric and non-symmetric case. And then he also proved sort of a very suboptimal bound in the symmetric case using sort of like generalized parallelograms. Another really beautiful paper of his. Okay, and then we go to the 50s. There's a very nice observation by Rogers Shepard, which I don't know if they actually observed, but it's sort of stated in Bourgain-Millman, attributed to Rogers Shepard, that any estimate that you can get on the symmetric Mahler conjecture immediately implies half of that for the non-symmetric case. So basically, it's yeah. If you know, so if you know the Mahler or the so-called Bourgain-Millman inequality with constant C for symmetric bodies, then you also know that for non-symmetric, for all bodies with a constant which is worse by a factor of 2, factor of half. Sorry. So okay, and Bourgain-Millman used this to reduce their proof to just considering symmetric bodies. So they showed for symmetric bodies that they have well, a non-optimal constant, but really sort of the closest result that existed until that time to Mahler's conjecture. So after Bourgain-Millman, essentially the Mahler conjecture is just reduced to improving this constant, showing it's equal to 4 in the case of symmetric bodies, and essentially E in the case of general bodies. And this theorem has been given many proofs since, and sort of keeping track of who has given the best constants, you have this sort of history here, or a partial history with various people, and the best constant to date is due to Cooperberg and in a completely different approach by Bernsen, and the constant they can get is pi. So it's getting close to 4. So it's pretty good already. And this implies by the remark on Roger Shepard, a constant pi over 2 for the non-symmetric case. Okay, now for the ball, well, the Bourgain conjectures really, it's I wrote here ball just because you can see the strong form first stated in written form in the paper of Ball, but this is really Bourgain conjecture. So very shortly after the conjecture was stated, Millman Pajor showed this kind of suboptimal bound. So instead of a constant to the power n, a constant over n to the power n, and then the non-symmetric case was done by Dar, and then various improvements. So Bourgain essentially reduced it to square root n, but there was some log factors. And then Powers did it in general case. Klartag then removed those log factors. And then in the last 2 years, there's been really sort of huge breakthroughs, and I'm really not knowledgeable about these proofs, but I just wanted to give credit here. And the most recent, as far as I know, estimate is log n in the denominator. Okay, so this conjecture of Bourgain is considered sort of a much harder conjecture than Mahler, and here, as you can see, that there is no analog of the Bourgain-Millman theorem. So the Bourgain-Millman theorem here was known a long time ago, and on this side, it's not known. So I mean, it is pretty good to have log n, but it's not the same thing. So that's kind of where things are at. And again, I say that I really not expert on this, so I just wanted to survey this, okay? And so now I want to just review a few things from convexity, basic things, but in this particular form, they're going to be helpful. So first definition of the norm associated to a convex body. Okay, so it's standard definition, and then the support function. Okay, and then the polar body can be written as the sublevel set of the support function. Okay, so this the support function is homogeneous function, and this gives us this equality here that HK is just the norm of the polar body. Okay, now when I say norm, of course, there's a little bit of impreciseness because unless the body is symmetric, it's not actually a norm in the sense of being a norm, like you put a real number and you can take the absolute value of that number out. So that it's only positive homogeneous. Okay, so it's not exactly a norm, so I write here norm in quotes. Okay, so that's just to keep in mind. Okay, and then there is this useful tool to use polar coordinates, and this gives a nice relation or a nice formula for the volume in terms of the spherical integral. So so this is again very well known, but just it's something that I will use maybe a couple times. So okay, and then finally there is a very sort of classical and important observation is that the volume of the polar body, using this trick here or using this formula for the volume in spherical coordinates, can actually be written in this very nice form in terms of the support function. Okay, any questions? All right, so I'll probably come back to these formulas.
Yanir, can you repeat the comment regarding the norm? You said if it's symmetric, it's a norm, is it actually?
Right. So when we say norm in analysis, we usually mean that right. So if I have a norm, then I look at the norm of lambda times x, and this should be equal to lambda times norm x for lambda real, right? So if the body is symmetric, this works fine, right? So but if the body is not symmetric, then it's only going to be true if I put lambda here to be in R plus. Okay, so if you have a norm function which satisfies this, we don't call it a norm, we call it a norm, right? Like that. Okay, does that make sense? Yeah. All right. So good. Okay, so we go to 2012. There was really a pioneering paper by Nazarov, and what he did was to relate the Mahler conjecture to the study of several complex variables and the Bergman kernel, so tube domains. So here, what he did is he took a convex body in Rn, and he looked at the tube above it, which is a pseudo-convex domain in Cn. Okay, so here it's just convenient to do things like this. So we put k in the second, in sort of the imaginary coordinates. And what he showed is that if you have lower bound on the Bergman kernel of this tube domain, it implies a lower bound on the Mahler ball. Okay, and so let me just make a little kind of flashback to recall what is Bergman kernel. So the Bergman kernel of a domain in Cn is basically characterized by three properties. It's a function on the product space, which is holomorphic in the first variable, anti-holomorphic in the second variable, and it reproduces holomorphic L2 functions. Okay, so that's just standard definition. Maybe you could say definition theorem, because this it really says that there is a unique such function. Okay, so just a couple of things here. So this Bergman kernel is because of the first two properties, it's going to be real on the diagonal. Okay, and then I was a bit vague about L2 with respect to what. So here I just mean L2 with respect to the Euclidean norm, the Euclidean measure, and but Bergman spaces are useful also with respect to other kind of measures. So and we'll see that later. So I just mentioned that. Okay, and so good. So that's that. Okay, and so in that slide I used B, but here unfortunately I used another letter. So also K is used a lot of times for Bergman kernel. Good. So okay, so let me discuss Nazarov's idea a little bit. And it's a really nice interaction between convex and complex, I think, and also it's another beautiful paper to read if you are interested in convex and complex geometry. So very well written short paper. So what Nazarov observed is that, well, there's the well-known old formula for Bergman kernels of tube domains, and it's written in this way, okay? And we restrict to 0, 0 because that's, in the symmetric case, that's enough, which is what Nazarov considered. In general, you need to look at the barycenter here instead, but it's not a big deal. So just for simplicity, let's look at 0, 0, and then the Bergman kernel has this nice formula. I mean, it's sort of nice as an acquired taste. When you first look at it, it doesn't look quite nice, but it's this integral, and then you have another integral in the denominator, and this is over sort of the real part of the tube, and this is over the imaginary part of the tube. But anyway, it is a nice formula, believe me. And he made this observation that this J here in the denominator actually can be related to the support function. Okay, so the proof is really not hard. It's almost like one line or maybe 2 lines. But once you realize this, then you can combine these 2 things, and you get pretty immediately a lower bound on the Mahler volume in terms of the Bergman kernel. So I wrote it down here with the exact constants. And this is not the whole paper. I mean, of course, so if this was the whole paper, it would be very short. But what he then went on to do is to actually obtain bounds on this Bergman kernel using Hormander's d-bar equation and Hormander's L2 estimates for the d-bar equation. So he constructed some L2 holomorphic functions on the tube domain that give then a lower bound on the Bergman kernel. So the Bergman kernel is has many characterizations. It's one of those objects which is just so important in mathematics that it can be characterized in many ways. So one way was what I showed in the previous slide, and another way is to say that it's the supremum over all L2 holomorphic functions, and where you take the ratio of the L infinity norm and the L2 norm. Essentially, then, in order to show a lower bound on the Bergman kernel, it suffices then to find one L2 holomorphic function, just one, for which you can control the value at the origin, and you can control its L2 norm, and that gives you immediately a lower bound on the Bergman kernel. So lower bounds on Bergman kernels come up in many instances in complex geometry, and so it's something that complex geometers deal with in many situations. But I believe it was new to kind of insert it into the Mahler conjecture discussion. Okay, so that's Nazarov, and now I should have mentioned my collaborators. I actually cut it from the first slide because I wanted to. I cut the title and the thanks to the organizers and the collaborators to fit into the small screen. So when I say our idea, this is joint work with Bourgain and Vlasis Mastrantonis, who is a PhD student at Maryland. So Okay, and so basically, our inspiration is Nazarov's work, and then subsequent revisitation of it by Zbigniew Włodzki. So there is this nice observation of Nazarov that this J function that appears in the formula for the Bergman kernel of tube domains is somehow has some inequality to the classical support function. So what we observed is that actually there is sort of a reason for this, maybe a kind of a more deeper reason why this is true, and this is just because this J functional essentially can be rewritten as some sort of L1 support function. Okay, and so we make this definition. This function here is not new in convexity. It appears in many papers before. It was really never just kind of called this way, but it appeared in many papers. And so really the thing here is not to define it, but to put it in this context. Okay, so when you make this definition, then and you do a little bit of manipulation, you see that then the Bergman kernel that previously had this kind of a little gnarly formula now suddenly takes a very nice formula just in terms of this L1 support function. Okay, so let me just go back first to the definition. Why call it L1 support? Because, well, if instead of this formula here, we put a p in the exponent and divide by p outside, that would be kind of an LP type support. And if you let p then go to infinity, you will just recover the classical support function. So let me just remind you that this is the formula for the classical support function, just the supremum over x dot y with x and k. Okay, so supremum is like an L infinity norm. Here we're looking at an L1. Okay, and you can ask why put the log in the exponential and not just kind of look at the integral over x dot y, maybe absolute value. So these kind of objects have been studied before as well, but then there's some differences and disadvantages, maybe some advantages. But one disadvantage is that if you well, let's say this way, one advantage of doing things this way is that if you put the p and then divide by p outside, you really take the limit, you really recover the support function, not kind of absolute values of the support function and things like that. So you can really treat symmetric bodies and non-symmetric bodies kind of in a unified way. But that's kind of after the fact. I mean, the real motivation for us was just that it fits in nicely into the Rothaus-Kurani formula. I mean, this is the formula from the 60s for the for the Bergman kernel of tube domain. It's very well known, and it just kind of rewrites it in a more convex friendly way, let's say. So okay, so thinking about it that way, remember we had this slide before, maybe I recall this here, where we had this formula for the volume of the polar body as e to the minus the integral e to the minus support function. So once you have kind of a new support function, you can then immediately define new Mahler type volumes. So the L1 Mahler volume is just going to be defined like this. Okay, and when you write it this way, you see that Nazarov's inequality between the Mahler volume and the Bergman kernel just becomes something like this. Okay. So okay, so let me go on to next slide. Okay, and so that's all nice, but all we did is just rewrite some things and introduce more notation. So what did we do here? So so if we want to I mean, there's two ways you can take this. One is you can say, well, I would like to use complex analysis to solve problems in convex analysis, or you can go the other way around. And ideally, you would want to go both ways. But first of all, I mean, we have the complex object here, Bergman kernel, and we want to then have some convex understanding of it. Okay, and so let's use convex to say something about complex. This is the direction. So does this object, which is really like a Bergman kernel, does it have a convex geometric meaning? Okay, so maybe I should say convex. Okay, and so it turns out that indeed it does. So remember that we have this in the classical support function case, we had this integral was n factorial times volume of the polar body. So really, is there some kind of LP type polar body that will have this as its volume? Okay, and so yeah, so this is either a definition or a theorem, depends how you kind of look at things. But yes, there is such a body, and the body is defined in terms of this norm with quotes, and this norm with quotes is given by this formula in terms of the H1K. So, and in this polar body, or the L1 polar body, as we call it, has a lot of the nice properties that usual polar bodies have. I just listed a few here, but it's compact if and only if zero is in the interior. It's symmetric if the body is symmetric, and there's many other properties that carry over, like Santolo point and Santolo inequalities and things like that. So, okay, and now if you then go back to what I was saying. So yes, there is a convex geometric interpretation of the Bergman kernel. So it's given as the ratio up to some factor of the volume of the L1 polar to the original volume. Okay, so so now I want to motivate this a little bit more, because if you've never so if you've seen these kind of things before, this is kind of almost trivial. But if you haven't, you're just like, why would you define this way? Okay, so I'll do that in a second. But before I do that, I just state some kind of natural generalization of this to LP, which I mentioned, but I didn't state it. So if I now put the parameter P here and 1 over P outside, then I get the so-called LP support function, and then I get also an LP Mahler type volume. Okay, and this operation of going from K to K P polar is called LP polarity. And okay, now there are some things that you lose when you do this kind of operation. Unlike regular polarity, you do this twice, you do not go back to your original body. Okay, so I have a proof by picture. Let me show this to you. So here you see the thing in the middle is the diamond in dimension 2. It's the polar of the cube. Okay, so this thing in the middle is the usual polar, but the things you see around it, these are LP polars of the cube, yeah, for other finite values of p. And as you can see in the picture, the LP polar body is a smooth body, as you can expect, because it's defined as an integral. You can differentiate out of the integral sign as much as you want. And so these are smooth bodies. And so if you do it twice, you're still going to get a smooth body. So you're not going to get the cube that you started with, the cube. Okay, so that's kind of proof by picture. And then you can state some conjectures, sort of the natural analogs of what Mahler conjectures are in p equal to infinity. All right, so okay, so again, these look just exactly the same as Mahler conjectures. There is one subtle difference that I'll mention in the next slide. Okay, so okay, so here I just wanted to since this is a mini course, really, and not just a lecture, I can be more pedagogical. Okay, so the definition of the norm of the polar body, I have it here. Here. So this is in the case of p equals to 1, but it's the same definition for every p. You just, instead of 1 here, you write p, and you use the LP support function. So I want to motivate this definition. Okay, so the first thing would be that if I put here just p equal to infinity, which function, then I should really just recover here the support function, right? Because the polar body is defined as hk less than equal than 1. So if I'm going to define the norm, it should sort of at least recover that. Okay, so okay, and so that's kind of the usual way to define the polar body when p equals to infinity, right? We would just look at the support function less than equal than 1. That's the polar body. So why cannot you just do that for other values in p? Okay, so the problem is that the support function is homogeneous, while the LP support function is not. I mean, it's defined in terms of this log of an integral. There's no be homogeneous. I mean, you put some, multiply by some number, it goes into the integral in some funny way. It will not be homogeneous. So if you check the formulas that we had before, right? So we our whole premise really is that we want HPK to satisfy this condition. So we want that kind of integral to recover the volume of the whatever the p-polar body is. And so if that's going to be true, you would write it as level sets here, but since this is not homogeneous, you cannot just do what you do in the homogeneous case and kind of relate this to this level set. So Okay, and so that's kind of why it doesn't work to do that. But what does work is to go back to our volume formula, classical volume formula for any convex body in terms of its norm. So we had this in a previous slide, so I'm just going to go with it. Skip it. The proof, we already looked at that. That's the volume of L. Volume of L. So and it's written in terms of this integral over the sphere. So so now if we want to impose this condition, then all we have to do is really write this in polar coordinates and make it look like this, and then we'll see from that what the norm has to be. Okay, and so you do that, and there's a little bit of algebra here, but you end up with this kind of expression, and you compare this expression to this formula here, and you see, oh, I'm going to define this to be my norm, and that's what we do. Okay, and so this is this goes back to Ball's thesis or something like that, the idea of taking a function and associate to it a norm. Okay, and so this is kind of the motivation if you've never seen this before. Any questions? Okay, so all right, so okay, so there we go. So LP polarity is maybe an acquired taste, but I guess I like it for its connection to complex analysis, the fact that L1 polarity recovers the theory of Bergman kernels on cube domains. But there's another motivation maybe for people purely in convex geometry, which is that which is the symmetric Mahler conjecture. So the symmetric Mahler conjecture, for many years it was just called the Mahler conjecture because that's what people were interested in, and the non-symmetric one was not really a thing. But there is a difficulty in the symmetric Mahler conjecture compared to the non-symmetric Mahler conjecture, and this comes up in geometry and in many settings where you look at problems that have some sort of big symmetry group, and you're trying to apply calculus variations or some functional analysis to understand extremizers of the functional, but there's this symmetry going on, and so what the symmetry does is it multiplies the number of extremizers. So for the upper bound, which is Santelow's theorem, the extremizer is the two-ball, and the two-ball is sort of, maximally symmetric in any way you can think of, and so there is kind of no problem there because that you apply this kind of symmetries that are inherent to the problem, and you don't get other extremizers. But for the minimizers, you do. And so if you take the cube, that's going to be one minimizer, supposedly, and then you take the polar of that, you get the diamond, that's another minimizer, and in higher dimensions, they're not affine equivalent. And then because of the tensorial nature of the problem, you can also take products of cubes and diamonds in lower dimensions, and those are other minimizers. So there's a lot of minimizers. As the dimension grows, really becomes a lot. So so Tao said that one of the main reasons the symmetric Mahler conjecture is difficult is that there are many distinct extremizers. So that's kind of a thing in the about the symmetric conjecture. Okay, now the maybe the nice feature about the LP polar or the LP version of the symmetric Mahler conjecture is that there is no longer the duality, or the polarity is no longer a duality, LP polarity. So and so in some sense you break the symmetry, and we believe that indeed the LP Mahler conjecture in the symmetric case should have a unique minimizer, just the cube. Okay, and so maybe that is, I mean, just maybe that could make that kind of conjecture easier to study. I don't know. At least it gives some hope. Maybe you can study the LP Mahler conjecture for finite p. There's no issue of symmetry, and then you take the limit as p goes to infinity, you get the original Mahler conjecture. So yeah, so just that's the thing I wanted to mention, and I guess
Sorry, Yanir, can you please repeat that point? So are you saying that for the LP versions, you're expecting unique minimizers, and then
right, yeah. So that's what I was saying. So here, this is just a conjecture. Again, it's a lot of conjectures, but the conjecture we have is that for the LP Mahler volume, there is a unique symmetric minimizer, which is the cube. Okay, and then you can do numerical simulations, and which we did, and you see that indeed the cube has smaller LP Mahler volume than the diamond, for instance. So that's kind of just kind of numerical evidence, maybe, but and this is actually also motivated by work of Dvorsky on Bergman kernels, who noticed also numerically these kind of things, for that the Bergman kernel for the tube domain is smaller than the one for the diamond.
so can I ask you, I mean, this may be already obvious, maybe I missed this, but is it obvious that if the boundary is just smooth, you just cannot be an extremizer, a minimizer? I mean, in these
no, in the previous slide with the smoothness, I was just saying that the LP polar body is always smooth of any body.
Saying that you, I mean, in terms of finding minimizers, can you say that they will never be smooth everywhere? Can that?
That the minimizer cannot be smooth. Yeah, so I don't know. Yeah, there is such a result in the classical Mahler case, and I don't know of in the LP case. I haven't shown that, but that would be nice. Yeah.
And maybe one final request, can you just push the page up a little bit, because I think we are missing the last line. No, the opposite direction.
Yeah. Yeah.
Oh, great. All right.
Yeah. Okay. Yeah. So I should also mention that one more insight that we get from this kind of conceptual approach is that, well, in Nazarov's paper, he obtained certain lower bounds. I mean, you have to run this kind of Hormander L2 estimate machine, and you get some estimate, and then there's always kind of the hope that, well, if you ran it a little bit better and you find a little bit better L2 holomorphic function, you'll get a better estimate. And so in his paper, it was left open, maybe the method really can just be improved and maybe obtain the Mahler conjecture itself or something better than what he obtained. So but this approach shows you actually exactly how far you can go with this, because I have this on a previous slide. Right, so I have this here. So if you look at the bottom, the Mahler volume is Nazarov's inequality basically shows in this rephrasing that Mahler volume is bounded below by the L1 Mahler volume over 4 to the n. Okay, and so if indeed you believe the LP Mahler conjectures, then what you see is that here this should be bounded below by m1 of the cube, and so that's kind of the best you can do here, and that's not going to give you the constant in Mahler's conjecture. It's going to give you something less than that. So this all I'm saying is that this just shows that the Nazarov approach to the Mahler conjecture was really an approach to the L1 Mahler conjecture, and so it cannot give the Mahler conjecture.
I have a question.
There's a question, Yanir.
Actually, to what you were asking. Okay. Were you asking in the classical Mahler conjecture, one cannot expect to have for the lower bound points of smoothness?
I was asking, not just points, I was asking for the LP Mahler conjecture, whether they knew the minimizers could not be smooth.
Because for the classical one, we know that if you have one point on the boundary where even the generalized curvature is strictly positive, then this cannot be a minimum.
Okay. Thank you. All right, Yana, you can continue.
Okay. Right. So I know it's not so easy to follow these kind of somebody talking on Zoom. So I kind of have a lot of slides left. So and since I'm giving two-part lecture, I think maybe it's safer to start the next part on Bourgain conjecture to start it tomorrow. And so if that's okay with everybody, maybe it's a good point to stop then. Yeah.
Sure, that's fine. Yeah, okay. So, are there any questions?
One question is there any relation between the L1 Mahler volume, LP Mahler volumes, and so on? Is there any obvious relation? Like you should.
Yes, that's a really good question. Yes, so there is as P goes to infinity, they converge to the Mahler volume, and then there's also some easy. So there was this observation by Nazarov who showed that which motivated our definition really, and he showed that the L infinity Mahler volume using some Jensen inequality can be bounded below by the L1 Mahler volume, and you can do that basically for any MP. You can show it's bounded below by MQ if Q is less than P with some constant depending on P and Q.
But the convergence, is it, I mean, which direction, sorry, is it from, if it's from below? Or?
Are they increasing?
Yeah, it's monotone, right? So if you look at the definition of the support function, it's kind of pointwise monotone going to the supremum norm. which is the classical support function. So that's pointwise monotones of the convergence also.
I had a question. I mean, so you said that this LP dual that you have is not really a duality operator. So then if you keep hitting it with the same thing, does that ever stabilize, or you just get a different object every time? I mean, you kind of have a new Mahler volume every time, right? Every time you hit it with a duality operator. What kind of happens to those products?
Yeah, that's a great question. I have no idea. I would imagine that maybe it makes sense to normalize
Right.
the volume every time you do it, and maybe it has some nice iteration property. I don't know. I think it's a really nice question. Yeah.
Are there any other comments or questions? All right. So if not, let's thank Yanir again.
Thank you.
All right. So we have a couple of a few announcements before we head out for lunch. So all of you who've registered, you would have received an email regarding the conference dinner. Thanks. Which is on Monday, and there's an excursion planned for Sunday. So we have, but we have 3 sign-up sheets, right? So, oh no, sorry. We have 2 sign-up sheets. One is for the dinner.
One sign-up sheet which has both of them.
Oh, so there's there's one sign-up sheet which contains sign-up opportunities for both, for the dinner and the excursion. For the details on both of these, please check your email. And there's something to do with the travel reimbursement.
Yeah. So I think for outstation participants, we are informed that we will be reimbursing your travel.
Indian.
Indian, right. And so you can find the sign-up sheet and the travel reimbursement forms are here. So travel reimbursement, you have to fill up the form and attach the necessary documents and hand it over to you. And if anybody needs a participation certificate, please email us with the subject participation certificate, your name and affiliation details.
That's what I want. All right, so Yanir, we will see you tomorrow.
Okay, see you tomorrow. Thank you.
So make sure I announce that. Yeah, so lunch will only get served at 12:30, so we can just have a discussion session or whatever people want to do. And we'll restart at 2 o'clock.
This is a dusty job.
Okay.
Dusty job.
He has sent it all the way from the.
Yeah.
I am out of the place.
I don't know. If it helps with the stats, so you got information on that. Yogesh, can you forward the email? He's gate crashing.
I got it.
For everybody. I have.
Yes.
Yeah, it's all the point for seeing about it doesn't matter
So you actually get more marks. I know, but I'm still not. You don't not
so that whatever you want, you have.
I also
Yeah, uniform I don't know. So for yeah, uniform I don't know because there then C0. Oh, maybe I don't know, maybe not in C, but that's the thing that if I get suspicious that you don't want to test based on the behavior of this one. I mean, so the positive kind of thing would be there that then we don't need either boundary or maybe no grades. Or it could happen that then you just come out with maybe in your case, if you don't have the format, very strong.
Yeah.
I mean, I think you can even have